took a long time.
Good, but this is how it's done.
Yeah, I'll show you that in math modeling. So
So, would everyone mind unmuting yourselves for a moment?
sure. What's up?
Just give me a second here.
Happy birthday, Jalen.
Thank you.
So, singing doesn't work all that well over Zoom, but let's try it anyway. Ready? Happy birthday
Birthday
to you. Happy
Happy
birthday
birthday
to
to
you. Happy birthday, dear Jalen.
Jalen.
Happy
Happy
birthday
birthday to you.
you.
Thank you.
I'm gonna blow this out for you.
Go for it.
Is that a cinnamon roll?
What's that?
Is that like a giant cinnamon roll?
Actually, it's an Asiago bagel from Panera.
Nice.
All I had.
Can't go wrong.
Okay. So remember, we were talking about eigenvalues and eigenvectors.
Random question. Did you just have like a random candle in your office?
What's that?
Did you just have like a random candle in your office?
No, you told me it was your birthday on Friday. I mean, you told me it was going to be your birthday today on Friday.
Oh yeah, I forgot about that. Thanks, Sakura.
You're welcome. Yeah, I don't usually keep a lighter or a bagel or a candle in my office. No, for emergencies. So remember what an eigenvector is. An eigenvector for a linear function, we've been talking about matrices, but it works for all linear functions, is a vector which gets mapped to a scalar multiple of itself. So given a linear function, T goes from some vector space to itself. We've been using, if our vector space has been Rn, we've been using an n by n matrix A, but it works for any linear function. So given a linear function, an eigenvector is a vector lowercase b, and don't forget to put your vector symbol over the lowercase b, such that T of b, so like A times b if you like, in the case of an Rn and using an n by n matrix, is just some scalar which we've been calling lambda times the original vector. In other words, it's a vector which gets mapped to a scalar multiple of itself. It's taken to a scalar multiple of itself. And lambda, that number, that scalar, is called the eigenvalue.
did you need to write down t equals v to v like under the linear given a linear function?
Here,
No, on the top.
t,
Yeah, there.
this says t and then colon, and then v.
Oh, colon.
Yeah, that's a colon, and then v.
I thought it said equals.
No.
Okay.
How's that?
Thank you.
Sure, no problem. Always ask if what I write on the board isn't clear. So in case it's been, I mean, you see this notation like in a calculus class. This just means that t eats things in v and gives you back things in v. Like in calculus, you would see like a function goes from the real to the real. So the domain is in the real numbers and the range is in the real numbers. So for example, we've seen a bunch of examples like this. Let's say A is the matrix 1, 1, 1, 1. And T colon goes from R2 to R2 by T of X is just A times X. We've done this exact example before, then say B equals 1, 1 is an eigenvector for T. Because T of 1, 1 is just that matrix A times 1, 1. And the matrix A is 1, 1, 1, 1. A lot of ones floating around here. And if we multiply this out, 1 times 1 plus 1 times 1 is 2. 1 times 1 plus 1 times 1 is 2. So this is just 2 times the original vector. So for most vectors in R2, if I take t of them, it doesn't give me a multiple of the original vector. But for the vector 1, 1, it does. It's just twice the original vector. So this is my eigenvalue for 1, 1. And we know by now that every multiple of 1, 1 is going to be an every non-zero multiple of 1, 1 is going to be an eigenvector with exactly the same eigenvalue. And there's another eigenvalue floating around too, which you've also seen. It happens to be 0. So I want to make a few more comments about eigenvalues and eigenvectors. Mostly we've been doing them with matrices, but it works for any linear function. So let's take a look at another example that looks very different, but uses exactly the same ideas. Consider the following vector space. It's called C infinity. Let me just say C infinity of R. I have, you should know what that means. I'm about to explain what it means. This is all the infinitely differentiable functions, the real to the reals. And even that might not seem too clear. I'm going to explain what that means too.
What does it say under consider? I'm sorry.
So it's a C with a subscript infinity, and then in parentheses, I have an R with a double bar down the left-hand side, like the real number line.
Oh, okay. Because from here it looked like it says cooler, but without the E.
It looks like it says what?
It looks like it says cooler without the E.
Cooler. Yeah, I'm in the mood for a picnic. So, for example, a function like x cubed minus x plus 5 is in C infinity of R. Why? Because I can just go ahead and keep taking its derivative forever. F prime of x is 3x squared minus 1. F double prime of x is 6x. F triple prime of x, 6. The fourth derivative of x is 0. The fifth derivative of x is 0, and it's 0 forever after. But I can just keep taking the derivative forever. Sine of x is in C infinity of R. Because the derivative of sine is cosine, the derivative of cosine is minus sine, derivative of minus sine is minus cosine, derivative of minus cosine is positive sine. You can just keep taking the derivative forever. So most functions you studied in calculus, as long as they are nice, they're sort of really, really smooth. This is basically the really, really smooth function. So C infinity of R are the really smooth functions. So most of the functions you studied in calculus. All the polynomials, sine and cosine, and let's see, the exponential function, they're all in there. So this is my vector space. This thing is going to be my vector space. So C infinity of R, let me just write that down, is a vector space. If I take two really smooth functions, like x squared and sine x, and I add them, this is just x squared plus sine x. You did this in pre-calculus. You can take two functions and add them. And if this is a really smooth function and this is a really smooth function, you add them, you get a really smooth function. That shouldn't be a huge mystery. If I take a function that's really smooth and I multiply it by a number, I get another really smooth function. So the set of smooth functions is a vector space. Set of really smooth functions is a vector space. It's not the kind of vector space we're used to thinking of. We're used to thinking of like R2 and R3 and R4 and R10. This one happens to be an infinite dimensional vector space. There's no finite basis. And there are linear functions. We can find linear functions. From the really smooth function, so that's a colon again, to itself. From the really smooth functions to the really smooth functions. The one that you know best you haven't thought of it as a function before, but it's certainly a perfectly nice function. I'm going to call it d. And d takes a function and just takes its derivative. So for instance, d of x squared is 2x. It eats a function and gives you back a function. It eats a vector in this vector space. The functions are vectors. And it gives you back a vector in the vector space. It gives you back a function. So the functions in these vector spaces are the vectors. X squared is a vector. 2x is a vector. Now, we know that D is linear because of the first two rules you ever learned about derivatives. We know that D is a linear function because the first two derivative rules you learned before you even got to like the power rule. The derivative of a constant times f, so, is just the constant times the derivative of f. That's the first rule. And the second rule, the derivative of the sum of two functions is just the derivative of the first one plus the derivative of the second one. You know, it's more complicated for products, but for sums, it's easy. If I, for instance, for the second one, if I want to take the derivative of x squared plus sine x, you know that's just the derivative of x squared plus the derivative of sine x. You don't even have to think about that anymore. Derivative of x squared is 2x, derivative of sine x is cos x, put a plus sign in the middle. Only thing that might look a little bit new here is writing d for derivative instead of like prime. So because of these two things, taking derivatives is a linear function. It eats these functions, these vectors, and it gives you back a function. It gives you back a vector. In senior seminar, I had to get rid of this talk because we changed the format of senior seminar, but I used to give a talk which basically the point of it was to blur in your mind the difference between functions and vectors, thinking of them as the same thing. Thinking of a vector as a function and a function as a vector. Is everybody okay with this D operator that just eats functions and gives you back functions, and it's linear because of these two, the most basic derivative rules? Cool. Okay. So let's find some eigenvectors for D. And their associated eigenvalues. Can you think of a non-zero function? Remember, the zero vector does not count as an eigenvector. Can you think of a non-zero function such that when you take the derivative of it, you end up with a multiple of the original function? And that multiple could be 1 if you want.
E to the x.
E to the x. So f of x equals e to the x is an eigenvector for D, because D e to the x is equal to 1 times e to the x. So here's our eigenvalue. Lambda equals 1 is the associated eigenvalue. Can you think of another one?
E to the 2x.
E to the 2x. So call this. So this is also an eigenvector for D. The derivative of e to the 2x using the chain rule. Derivative of e to the blah is e to the blah. And now we have to multiply by the derivative of blah. Derivative of 2x is 2. So that's 2e to the 2x. Here's our eigenvalue. So lambda equals 2 is the associated eigenvalue. And at this point, I think it's probably pretty obvious to you that there are infinitely many different eigenvalues. This doesn't happen with matrices. So, e to the Rx is an eigenvector for any R. The derivative of e to the Rx is just going to be R times e to the Rx. And so lambda equals R is the associated eigenvalue. Associated eigenvalue. And so D has infinitely many different eigenvalues. In fact, every R is an eigenvalue. Any real number is an eigenvalue for D. I want to show that 5 is an eigenvalue, I'll use e to the 5x. I want to show that negative 30 is an eigenvalue, I'll use e to the minus 30x. The only reason we can have infinitely many different eigenvalues is because the space that we're in is infinite dimensional. So in finite dimensions, so let's go back to n by n matrices. This can only happen because C infinity of R is infinite dimensional. That's the only reason we can have infinitely many different eigenvalues. So back in finite dimensions, so let's say A is an n by n matrix. We know to find all the eigenvalues for A, we compute. So we solve the characteristic polynomial. In other words, we take the determinant of A minus lambda times the identity and set it equal to 0. We've already done that for some examples. Taking the determinant of A minus lambda times the identity and set it equal to 0. So for example, for instance, our matrix A was, was 1, 2, 2, 4, we would take the determinant of 1, 2, 2, 4 minus lambda times the identity 1, 0, 0, 1. We've done something like this before, not with this exact matrix. And this is the determinant of 1 minus lambda times 1, so 1 minus lambda, 2 minus 0, which is just 2, 2 minus 0, and 4 minus lambda. And so that's just 1 minus lambda times 4 minus lambda minus 2 times 2. And we'll set this whole thing equal to 0 and solve for lambda. You can do this if you want at your leisure, but I want to make sure that you remember how to do it. what degree polynomial do we have here? If you multiply that all out, oh, I can't quite see your fingers. Right, that's a degree 2 polynomial, exactly. So this is degree 2. If A is an n by n matrix, the characteristic polynomial basically, since you have a lambda on each of the diagonal entries, no lambdas off the diagonal entries, the characteristic polynomial, the determinant of A minus lambda times the identity, is an nth degree polynomial. Which of course means that if n is any bigger than, like, say 3, this isn't fun to do by hand. If I have an nth degree polynomial and I set it equal to 0, what's the most number of solutions I can have? No, an nth degree polynomial. So for a second degree polynomial, it's definitely 2. For an nth degree polynomial, it's what? You're not going to be able to do this with your fingers, I don't think. If you said something, I couldn't hear you.
Oh, is it n?
Again, yeah. And nth degree polynomials, you know, nth degree functions cross the x-axis at most n times. So at most, an nth degree characteristic polynomial equation has n solutions. That you've known that sort of since pre-calculus, I guess. You know that a second degree polynomial, like a parabola, crosses the x-axis at most twice. A third degree polynomial crosses the x-axis at most 3 times. A fourth degree polynomial crosses the x-axis at most 4 times. It doesn't always cross the x-axis that many times. For instance, you know, y equals, let me say, x to the 4th plus 1 equals 0 has no real solutions. The graph of x to the 4th plus 1 looks like that. It doesn't cross the x-axis at all. But it has, any 4th degree polynomial will have at most 4, any 4th degree polynomial equation will have at most 4 solutions, and possibly fewer. And so an n by n matrix never has more than n eigenvalues. It never has more than n eigenvalues. So a 2 by 2 matrix never has more than 2 eigenvalues. It could have fewer. You've seen an example of a 2 by 2 matrix which has no eigenvalues at all, that rotation. You've seen examples of 2 by 2 matrix which have 1 eigenvalue. The identity matrix, the identity matrix has only 1 eigenvalue. Eigenvalue is 1. You know it's easy to read eigenvalues off a diagonal matrix. Just look at the matrix and look at the diagonal entries. 1. All I see. But they never have more than 2. A 3 by 3 matrix might have 3, it might have 2, it might have 1. Can you explain to me? This is sort of interesting. We know a 2 by 2 matrix might have no eigenvalues, right? It may have the matrix, the 90 degree rotation, 0, 1, -1, 0, clockwise, counterclockwise, I can't remember. 90-degree rotation. Obviously, if you rotate all vectors 90 degrees, no vector ends up parallel to itself, right? Because it's rotated 90 degrees. Its image is rotated 90 degrees. Can you explain how you know that a 3x3 matrix always has at least one eigenvalue, and if it has an eigenvalue, it has some eigenvectors. And therefore, some eigenvectors. So a 2x2 matrix doesn't have to have any eigenvectors. It doesn't have to have any eigenvalues. But a 3x3 matrix always has at least one eigenvalue and therefore some eigenvectors. How do you know?
You said, how do we know if there's at least one?
That any 3x3 matrix is going to have at least one eigenvalue and therefore some eigenvectors. How do you know?
For one, it's not a rotation.
Well, it's definitely not going to be, well, it could be a rotation. You can rotate things in 3 dimensions. You rotate around an axis. But the thing on the axis doesn't move, right? If I rotate around an axis in 3 dimensions, the thing that's right on the axis points in the same direction it was. It's an eigenvector. How do you know that any 3x3 matrix, any linear function on R3 is going to have an eigenvector and an eigenvalue? Let me ask you this. What degree is the characteristic polynomial going to have for a 3x3 matrix? Right, at 3. And what can you tell me about polynomials of degree 3? What can you tell me about any polynomial of degree 3? Any polynomial equation of degree 3? You have to go back and ask your pre-calculus self. What's true about any polynomial equation of degree 3? You know there are polynomial equations of degree 2 which don't have any solutions. X squared plus 1 equals 0 has no solutions. That thing never crosses the x-axis. What can you tell me about polynomial equations of degree 3?
Oh, it always crosses the x-axis.
They always, yeah, polynomial of degree 3 always crosses the x-axis. Do you remember why?
No, I just remember the graph.
Well, okay, so tell me about the graph.
Yeah, it goes like, I don't know, to the right, upwards to the right, and like
Well,
downwards
it
to
doesn't
the
have to
right.
go upwards to the right. If I have something like minus x cubed plus x equals 0, that one goes down to the right. That one looks like something like that. It can go down to the right. But what can you tell me about the ends of a 3rd degree polynomial equation?
It keeps going forever.
Well, so does this. These keep going forever
Oh,
too.
yeah, my bad.
What can you tell me about a 3rd
Go in
degree polynomial?
opposite directions.
Yeah, exactly. One end goes up and the other end goes down. It's got to cross the x-axis somewhere. So this is true because the polynomial, the characteristic polynomial equation, determinant of A minus lambda times the identity equals 0 for a 3x3 matrix is degree 3. And all degree 3 polynomial equations have a solution. In other words, their graphs cross the x-axis. All the stuff that you learned in pre-calculus and calculus is all helpful. You know, we teach mathematics sort of broken up into different courses with names, and it seems like they're independent of one another, but we just do that for convenience sake. You know, we put all the calculus into one class, or 3 classes, I guess. We put linear algebra into a class. We put abstract algebra into a class. It's just for convenience sake, so we can sort of check off things that you've learned, like on a checklist, and keep track of it easily. But it's all artificial. Math is basically one organic subject. In the same way that, you know, if I take some of your organs out, you know, you're not going to survive very long without your heart, or without your spleen, or without your liver, or without your lungs. You need them all. Math is like that too. So a 2x2 matrix may have no eigenvalues, and so no eigenvectors. It could happen. Plenty of 2x2 matrices do have eigenvalues or eigenvectors. A 3x3 is always going to have at least one eigenvalue. A 4x4, maybe not, maybe none, because even degree polynomials don't have to cross the x-axis. A 5x5 is going to have at least one. And again, it's sort of interesting to notice that that sort of agrees with what you know about geometry. If I have like a motion of the plane, a rotation of the plane, I might have no vectors which end up pointing in directions parallel to which they usually point. But if I say rotate three-dimensional object, if I rotate a three-dimensional object, the axis around which I rotate, that's always pointing in the same direction it was originally pointing. So there's always something which points in the direction it was originally pointing for a 3x3 linear function. What are we doing? That's a pretty good place to stop, I think. There's really only one subject left in the course, and many of you have seen the basis of this subject, no pun intended, before. If I asked if any of you had seen something like dot product in, say, a physics class before, or even a math class, has everybody seen dot product or something before?
I don't know what that is.
Okay, well, that's okay. We'll talk it over. So we're going to start from scratch. So we'll talk about dot product briefly, and then we're going to go into dot product's sort of older sibling, which is called inner product. An inner product is just a generalized dot product. But if you understand dot product, then you're going to understand this pretty well. Although for those of you that have studied dot product, you probably haven't been interested in exactly the sort of thing that we're going to be interested in now. And if you haven't seen dot product before, it's going to be no handicap at all. But that's the one last thing that we're going to look at. We're going to look at dot product, inner product, and then we're going to look at something called a orthonormal basis. You know what a basis is. We're going to talk about orthonormal basis shortly. So the stuff that's coming up all has to do with like length and angle. That's sort of what ties it all together. Length and angle. I know everybody knows what I mean when I say length. I know everybody knows what I mean when I say angle. So for those of you who are not in my next class, I will see you on Wednesday. For those of you who are in my next class, remember all this week, I'm just here to help you work on your projects. So feel free to come next class if you like. And if you want to just go and work by yourself, that is also fine. But I will be here to answer any questions that you might have. Are there any questions on this class? Okay, I will see you all. Yes.
Oh, I said no.
Okay, I will see you all shortly. Take care. Happy birthday, Jalen.
Thanks, Dr. O.